Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. We're on episode 25 already, which is surprising to me, but I love it. Still working on the xenowing, and a quick catch up from last week. I believe we were working on support for the simulator compiler in Kaze, and this last weekend I kind of pounded through and got that working. In particular, the feature that we were working on was Synchronous Memory Support. So I can show a bit of that API now. So let's see. Just doing the publish one because that's the easiest one to click on. Yeah, so now I've added this Mem Construct here. And the main point here is that if you have a module, you can create a memory and you give it the amount of address bits. So it's 2 to this many bits. Elements, and then this is the bit width for the individual elements themselves. So essentially this by this bits of memory. You can optionally specify initial contents. You can also optionally add a write port. You need one of these two things in order for the contents of the memory to make any sense ever. Initial contents are also not reset on reset. They're only initially when the system starts up, with which really only favors FPGAs, and that's fine because I can always change this API later, but that covers the use cases that I have in mind at least. There's only one write port allowed, and I've opted to be able to create multiple read ports, essentially unlimited with this API. And then you need at least one read port in order to get data out of the memory, otherwise it makes no sense to have it, so that's also a logical error. So basically I finished implementing that and wrote some quick docs. And in addition to that, then I started moving on to the actual system implementation. And the thing that I worked on in particular there was the Fifo. So in the old code here, which is still in RTL old, I haven't gotten rid of it yet. Looks like this. It's not that much code, and this is for a synchronous Fifo. And there's actually some interesting things here because this code looks kind of innocuous. You have reset and clock, you have these empty and full signals, so that this thing can report to its write side and its read side, actually read and write, essentially whether or not you can read more or write more to it. Read more from, write more to. And then, of course, the ports to be able to actually initiate a read or write. Again, same thing here where you have depth bits, so you have one of that many bits. And then there's also the data width here. And it looks okay. I'm not going to go over this code in too much detail, mostly because I actually really just want to show that there's a bug in this implementation. And I don't know if this ever actually surfaced with the old system. I do remember seeing some crash bugs that I couldn't quite explain, and I did suspect that something in the buses might be at fault. But I think I don't know if we ever actually hit this issue or not. But here, you'll notice that you're only allowed to write if you want to issue a write. You're only allowed to do that if it's not full, which makes sense. And I think before I had the logic to stop a write if the Fifo was full external to the Fifo, and I decided later to refactor and put all that stuff in the Fifo because I ended up having duplicate logic in other places. So it made more sense to me to disallow writes at this level. But you'll notice down here, it'll still actually write to the memory, even when it's full, as long as write enable is asserted, which is not correct. So the main thing here is not really to show that this was necessarily bad implementation, because I think, honestly, if I did this, it's basically fixed. But one of the advantages and one of the reasons why I wanted to do Kaze in the first place is because I wanted to be able to test a lot of these modules in Rust simulators, just because I thought that would be comfortable and nice to set up. And it turns out I'm pretty happy with this. So in this, no Chief Detector, it is still a Fifo. So stack is LIFO, last in, first out, but a Fifo is first in, first out. But they are rotating buffers. So there's a capacity, which is the buffer, and you increment the write pointers whenever you write, and you also increment the read pointer whenever you read. So if they're the same, then you either have an empty Fifo or one of them is wrapped around, which is why it also includes a count in order to track those explicitly instead of just relying on the pointers. But yeah, it's a really simple kind of structure, and it's pretty ubiquitous. In particular, that was something I used in the memory buses because, let me paint a little picture here, literally. If you have a system like this, and let's say this is some bus. So down here, you have this, and it's going to talk to some memory, for example. And then up here, you might have, for example, display DMA or some other kind of DMA, and then a CPU. Both of these are going to be bus masters, whereas this is going to be a bus slave. And so you need to do a couple things here. You need to arbitrate these. And if either of these are going to issue a read, you need to sort of issue the read, and it needs to go down here. And then this is going to get the data and then return the data. And once this data returns, you need to know where did that come from in order to send it back to the correct master. That's kind of the issue. And so the way I solved it previously is whenever you would issue a read, you would not only issue a read to the memory, but you also have a little Fifo here, which I'm going to draw like this. So here you issue the data, and then here you issue a 0 or 1 depending on which master it came from. So in this case, it would put a 1 in this Fifo. And then when the data comes back, you pair that data up with the value from the Fifo, and then you know, because they're 1 here, you would send this to this one. And that alone is not bad. If you have multiple masters and a single slave, this works just fine. However, if you have multiple slaves, you can run into a weird issue. So let's say this is like an LED interface. And let's say then here the latency matters, because usually if you issue a read, then on the following cycle, the data might come back. However, that's with latency, which I'll denote as, I don't know, I feel like using lambda, so we'll do that. Latency is 1. And then here, latency might be 20 cycles or something. And this can actually be a problem. So let's say the DMA issues a read, and it issues a read to the memory. So it issues a read to memory, and it pushes a 0 into this Fifo. And then let's say before this data comes back, the CPU, maybe on the next cycle, issues a read to the LED thing. And so that's going to put a 1 into the Fifo. Then what happens is the LED comes back with its data on the next cycle. And that's actually bad, because now this incoming data is going to pair with this master, which is the first thing that comes out of the Fifo, and it's going to send its data here, and then when the memory comes back with its data, it's going to send its data here. And so now both of these units here got the wrong data. And I don't think I had thought about this in the old xenowing, but this definitely is a potential issue. And I don't know if I ever ran into this, but again, I might have. And because in particular, I did have a system here where I had DMA that could actually read some memory. So I think my code was wrong in the system bus. I'm not actually entirely sure, because what I decided to do is just kind of rewrite all of the bus stuff and sort of build it more piecewise and test each piece individually, because this is deceptively complex. And this can be solved if everything has the same latency and like you serialize all the reads through this bus, then you're fine. But it's this variable latency that kind of kills you. And all of that is really a product of the fact that we're interfacing with DDR memory, where we don't have any control over that latency. So the way that I'm thinking about solving this is similar to how we have this sort of read return Fifo here. I still want to have that. But then I want to have this read return Fifo, which I'll actually draw here. So let's say this had 0 and then 1. And then also the data coming back from here, I'm going to stuff into individual Fifos. So there's one here, and there's one here. And so let's say this came back with B, and this one came back with A later. It wouldn't really matter, because what's going to happen here is that then something's going to pull this off into a little buffer. And so this is going to say 0. Cross that out. And then it's just going to sit there idling until it gets something back from 0, right? From this one. I think actually that's wrong, because this needs to return, that's which master it's going to, not which slave it's coming from. So already there too, we need to figure that out too. So I think each of these might even need another Fifo, which is, yeah, I think this is what I was thinking. You have a Fifo for which master it was, and then a Fifo for which, and then another one for which slave it was. So let's say 0 went to this one, and then 1 went to 1. And then what you'll do is you'll pull both of these out into a buffer. So in this case, we have 0, 0. And then even if this comes back first, it doesn't matter because we're always going to wait until we get something back from slave 0. And at that point, then we pull this data off, pair it back with this master, and then send it back. And then the next thing is that this 1, 1 would be loaded into that buffer. And then immediately we can pull this off and then do that. So the kind of downside of this is that it serializes all the results of the reads. So if one read is issued really early on that has really high latency, all of these other reads are going to be behind that. But if you make these FIFOs fairly deep, then at least you can issue a bunch more reads in maybe some common cases. So at the very least, the throughput should still be pretty good, even though the latency in some cases is going to be pretty bad. It's going to be dominated by whatever the slowest or whatever the slave is that has the most latency. But again, I think like better systems like this could be designed, but I think this is what I'm going for because it should be relatively simple to implement. But again, a lot of this hinges on this FIFO implementation being correct, and that's one of the reasons why I decided to revisit it. So I re-implemented the FIFO in Kaze this time, and it's still not that much code, but the most important thing is that, so I have in this RTL project this FIFO, and I also, in the sim project here, I made a project to mirror that, which is the FIFO here. And this has a build.rs script, which is going to generate code for that module. So it generates a FIFO, and it's parameterized in this case, so I call it FIFO, and it has 4 depth bits of 16 entries and then 32 bits wide elements. And then that outputs that code that's built with this module. And then I have in lib.rs, I have a bunch of tests that instantiate the FIFO and then do some basic tests on it. So things like when you reset, make sure it's empty. When you reset, make sure it's not full. Here, I think I tried to do a read when it's empty and then make sure it's still empty. And I do that a bunch of times just in case. Basically, I can do this write and assert that it's empty until I write all the positions, and then assert that it gets full. And then I do the same thing and then issue a single read and make sure it's not full then. Just basic stuff like that. And not that many tests covered here. But then in addition to that, I made this main RS thing so I could run this test. If I do cargo tests, it runs all these lib tests. But if I run it on its own, I can specify a random seed and a number of elements. And essentially what this will do is it makes a big buffer of num random elements. And it literally just has a write side and a read side. And the write side just sits and tries to push all these elements through. And the read side tries to read them all back. And in addition to that, I have, for every cycle, whether or not the write side can write and whether or not the read side can read is random and uncorrelated. So the idea is that kind of simulates some it kind of adds some non-determinism into the whole mix. And essentially, I just run this until I've read enough data. Essentially, push the whole buffer through the FIFO, and then I assert that the buffer that we got is equal to the buffer we started with. And I ran this for several hours, and I think I ran like 8,000 iterations or 8,000 different seeds, where num elements was like 1 million or 10 million or something. I don't remember what I had. And anyway, so I feel fairly confident in this implementation. However, I need to make it a little bit better. And there's essentially one case that I need to talk about. But first, hi to guys in the chat. W Writer, how's it going? Hey, Chief Detector. PSNF, what's going on? So the main thing that I need to cover is, I think I shared this last time. I use this. Hey, Static. I use this wave DROM tool. And I kind of talked about how the memories in the system are going to work. So this is actually how the buses are going to work, but the memories share a certain property with this, which is basically that if you issue a read, which I think is happening here, there's a read here to this address. And the idea is that you have this enable, so this would be like a read enable signal, and it goes high. And as soon as you have a cycle where read enable is high and the bus ready is available, in this case it's the FIFO that would assert that, but in a memory it's always just available. Then on at least the following cycle, I think here I simulated that it would be a couple cycles before a slave return, but essentially on the following cycle, we would get the data. And this actually differs from the old FIFO that I had, because the old FIFO had asynchronous reads. And there's several reasons why I don't want to support that in the new implementation that I don't really want to get into, but essentially it adds a cycle of delay. So before, it might actually make sense if I just take this wave drum thing and explain what I want to do here. So I'm going to do that actually. I think that works. We don't need a bunch of this stuff. This is a really cool tool, by the way. Let's see. So let's do a read. So the address and then read enable. So the idea is that at some point, read enable is going to go high. And in fact, we can get rid of data here and make this a 1. And then, let's see, we're going to get the read data and read data valid. Like this. Something like this. So I'll even use AD for the address. I like lowercase. And then .x here, I think. Yeah, that's cool statics. I'm glad you enjoy it. I think it's really fun. And it's a big learning experience for me, this whole thing. So I'll call this, I don't know, FF for the data. Doesn't really matter. But essentially, the idea is that eventually, this is what a read's going to look like. We're going to assert a read from a certain address, and this is what we put into the memory. And on the following cycle, the memory will return by saying read data valid is 1, or read data, and then also that the read data valid is 1. I think that was what I want here. I already don't remember how to do this. 3, I think, is what I do. Yeah, there we go. Just erase some extra cycles here because don't need them. Yeah, so this is what a read looks like from the memories that I've chosen to implement here. So yeah, we put in an address and a read enable, and then on the following cycle we get the data back. Now before this is called a synchronous memory, and so before what I had. And also the read data is only valid on the cycle following. So after that cycle, the data is essentially lost. This could have anything on it. And the old ones were like this, where as soon as you it's like on the same cycle that you issued this, the data would come back. And the main consequence here is that everything that needs to read from this needs to latch the new data on the following cycle. It needs to be aware that it needs to do that, and we need to account for that 1 cycle delay whenever we use these. So we have to design a bit carefully, but it's not too bad. Now for a Fifo, let's see. There's essentially one case. I don't know if it's very fast for me to describe it like this, actually. Let's go this read adder. But let's try, actually. Because it's... So let's say the write adder was going to be the same as the read adder. And we had read enable, so we're going to have a write enable too. So the main thing here, and I actually need empty and full signals here in order to properly describe this. I also need to shift some things over. So let's do this. Evil. Thanks for the follow. That, I think. Yeah, this is supposed to be there too. Let's see. We're almost there. In fact, actually, this I want to be back here, and we want to do this. We'll get to why that's the case. In fact, this one actually needs to be like this. And the read adder is the one that we need to be valid a cycle before. So before I explain this, we need a couple more things. Actually, we'll do another cycle at the beginning of here for all this stuff. So we need a couple more signals here. One of them is going to be empty, which is initially going to be just 1 because it's empty the whole time, and then there's full, which is going to be 0 the whole time. So this is the kind of interface that you'd get for Fifo. You have whether or not it's empty or full, and then you have these abilities to the ability to write or read. And the idea is that if you assert a write, so you have write enable with some address and then some data, we need to write data line here, don't we? Did I not do that? No, I didn't. I did the address. Yeah, so write data in this case should be FF because that's the data we read back later, right? So let's just talk about this write. We'll ignore the reads for a second. And in fact, I actually don't think I have a read data valid signal in this Fifo, so we'll get rid of that. Yeah. So initially on reset, you have this full condition is low because obviously the Fifo's not full, and then you have this empty condition that's high because it's initially empty. And let's say this has like more than one different elements in the Fifo, and let's say 2 because that's the minimum that I basically support because of the memories. So if we just look at a write, let's say we issued a write. In fact, we can even move these back again. It doesn't really matter. And we'll do the same for the data. I like this tool because it gives nice diagrams and it's not that hard to modify. But essentially, you can only issue a write. The write will only go into the memory as long as when you issue the write, full is low. Right? So just looking at the signals that we have here, this write will take effect because it's not full during the same cycle that we issue a write to this address and this data. I'm also going to put the address and data together like this. So this is a nice clean write. Again, ignore the reads. In fact, I can even do this for now. Cool. So this write would take, and then the only thing I need to change here is that empty should actually go low on the cycle following the write. And this is great. This is exactly what we would get. So let's say we did that. And then we would issue a read on the following cycle, for example. And let's not do this yet because I'm going to use that for teaching later. And then this needs to be shifted back 1. Yeah. So the idea here is you can only do a write if it's empty. And I'm going to actually move the full down here. You can only do a write when it's not full. So let me do this instead. Put the empty here. Obviously, I have not prepared for this, so it's a bit messy, but I think we're getting to a good explanation. Yeah. So initially, it's not full, so we can do the write. So as soon as we issue the write, we know the Fifo took that write. And then empty goes low, which doesn't really matter here. The main thing is that empty going low means that we can actually read from it. That's really the point that we have here. So then that's how the reads work. If empty is low and we assert a read, then we know that the read was valid, and on the following cycle we'll get the data out. This is how the Fifo works. And maybe it's actually better that for this Fifo interface that I actually do export a signal for data valid, but we'll see if we actually need that. I have a feeling that might be something we want, but we'll see. Anyway, this is fine. But let's say instead we wanted to do a read a cycle earlier. This is what we're kind of going to get at. Now this actually wouldn't happen, that this data valid would come back, or this data would come back. And the reason for that is that when we issue this read, the Fifo was empty. So that read wouldn't take. The Fifo wouldn't return the data. So if we tried to read back on this following cycle, we'd get garbage. Instead, what we want to do is since the thing that issued the read, it asserts read enable and read adder, and then it needs to check empty. So if this case happens where we try to assert a read while it's empty, which is actually the same if we try to assert a write while it's full, that will not take. And so what we need to do is we actually need to hold these signals for another cycle. Basically need to hold those until we get a cycle where this is the case, where we're asserting it and the Fifo was not empty. As soon as that happens, then we're going to get a cycle where on the following cycle the read takes. Right? I think this generally makes sense. But actually, this is wasting a cycle here in the case that the Fifo's empty. Because actually the way that the memory itself works is it's called a read-through memory. And the idea is that if you have a read and a write to the same position in the memory, which is what you would get if the Fifo were empty, that's actually a valid read, and the read's going to return the data that you just wrote. So we should actually be able to support the case where we have this. And what should actually happen is this empty signal, instead of going low there, this should actually go low as a consequence of the fact that we're writing to an empty Fifo. So within that same cycle, this should actually reflect that it's getting incoming data, and that the write's actually okay. So the fact that we're issuing a write while the Fifo is empty, this should actually work. And as you can see, then the read gets done a cycle earlier, and we can do that by virtue of the way that the memories work. Is that an okay explanation of kind of the issue I want to fix? Essentially this empty thing is the thing that we need to fix. Now the way we do that might be a little bit complicated, but I'm going to start the way that makes the most sense to me, which is to write a test for this. So if we'll just take a really simple one here. And so we make the new Fifo, we reset, and then we propagate signals so that the outputs are correct. And then what we're going to do is we're going to, actually, let's see. Or we'll do, I think I actually want to call this write through when empty. Yeah, empty Fifo is bad. Definitely true. I need to write this stuff more properly at some point. Because there's sort of a bigger picture thing that I'm going to get at eventually, which has to do with the bus implementation stuff that I mentioned earlier, and the different Fifos that are going to be used there. And essentially, if I'm able to read through the Fifo faster, then I will get away with having less buffers in the memory, in the bus implementation. And just like we're doing with the Fifo, like where I'm just pushing a bunch of data through this, I'm gonna write the same kind of tests for the buses, where I just do a bunch of dummy reads and writes through the buses and make sure data gets where it should have gone. And I think this is going to be a really effective strategy. And again, there's none of this that I couldn't have done with Verilator. But I just would have liked to write all these tests with a lot less plumbing and in Rust. So that's kind of cause for the rescue. Yeah, this tool is really nice. I need to start properly using it. The reason I actually started checking it out is because I started writing, and I'll publish like all of this as part of xenowing at some point. But the point is that this is just, I think it's a secret gist that I have right now. But I was just prototyping how I wanted the buses to work and the different signals. And as I wrote them in like a big table like this, I found out that this just wasn't that illustrative. So I started looking for tools, and it turns out WaveDrum exists, which is great. So I want to supplement that document with a lot of these kind of diagrams, and then that'll be part of the Wavesaver documentation. Not Wavesaver, xenowing. That's a different project, Jake. But yeah, I want to support this case where it isn't actually empty if we're writing to it on the same cycle that would have otherwise been empty. So essentially what I want to do is test two things here. The first thing I want to do is I want to say m.writeEnable is true. And we actually need to do a few different things here because we need to set write-enable is true. We need to set m.writeData is something. It doesn't really matter. I like to use a few different constants throughout the test, even though I think I'm using fadebabe a lot. Just because it keeps you from doing something stupid if you return like a test value or something in the implementation. But I think the Fifo... Okay, so by the way, here's another thing that's a bit tangential, but something I actually don't like about Kaze that I want to fix. I wanted to make it really short to write out like inputs and outputs. So I made this part of this kind of API where you kind of scatter inputs and outputs throughout the code where it's most natural to have them. And this actually kind of sucks because now it's really hard to get overview of what the ports are for this particular module. Now there is a way around that, and that's I can actually go in the target for the build, and I can look at the generated code, which has them here. So that's kind of my workaround for now, but that's something that should be fixed on the API level eventually. So always cool when you can use these tools and then find out things you want to change. Anyway, here's the same inputs and outputs. We have read enable, write data, write enable, and then the outputs from the Fifo are empty, full, and then the read data. And like I said before, there is no read data valid. It's assumed that read data is going to have valid data on the cycle after a successful read is asserted. And yeah, so that's what I want to do. I want to issue a write, or first I want to. Well, actually, we have another test to check that it's already empty, so I'm not going to worry about that. Although, actually, I do want to assert this because m.empty is true. And then what I want to do is by asserting a write while it's empty, right? We'll propagate the signals. And then this should at least tell me that it's false, right? So that's the thing that we want to do. And then what I want to do is I want to do m.read enable is true. And I think that's all we need. And then what I can do is m.prop, m.pause clock, and then we'll propagate the signals back again. And we should see assert equal empty is going to be true. And we should also assert the data that we get back on the following cycle. So m.read data is going to be dead beef. Hey, well, I'm doing great. I hope you're doing awesome too. Hope you're making some kick-ass shaders for revision. Maybe it's a bit early for that. But yeah, I think this test on its own kind of encapsulates what we want to describe here. And if I run this should fail. So I think I'm already in here. So if I do cargo test, that's all it will take. Yeah, there we go. So assertion on 145 failed because we expected, that's this one. We expected this to be false, but it was true because right now we don't have this write through implementation. Yeah, I'll be skipping revision this year. I'm a bit sad about it, but I think it's the right choice for me this year. I love revision, obviously, but I've been pushing it pretty hard. So, gonna make some other things. I'm hoping eventually to do a demo for the xenowing, which would be awesome, but for now, we're still building some basic stuff. Anyway, yeah, so this fails exactly how we expected it to fail, which is great. And so then we're going to go into the implementation. And let's see. I think this is not going to be terribly difficult, actually. We essentially have this empty here. And I think all we actually have to do is... it's either empty if the count is 0. I don't think I want to just do write enable, but that might be it. I don't think that's going to be it. Or is it not write enable, right? So empty is normally true, like if it's 0. So if it is 0 and write enable is true, then we want empty to be false. So that covers that case. But let's say that the count was 1, and then empty would already be false. And then or not write enable doesn't work. Because we want it to be false in that case. But then if a write is not being issued, then this will be that or true, and then empty will be true. And it's not empty. It has 1 value in it, for example. So that's not going to work. So I think we need to only do the write enable check if this is normally low. And for that, we can use this if construct that I have here. So if the count is 0, if the count is 0, then we want not write enable. Otherwise, we want low. I think this makes sense. So if the count is 0, then we want it to be low if write enables is high. And we want it to be high if write enables low. And if the count is anything other than 0, then we just want empty to be low for sure. I think this makes sense, and this might be all it takes, but I somewhat doubt it, so we'll see. Run the tests, and then now write through an empty fails at 153. So it got through this one, and now it fails here. Right, and it's because I don't think, where's the count? Yeah, so here, because write enable is high, the count should be incremented. And then here it was not empty. So if we read enable and not empty, then the count should have also decremented. And that should all have happened in the same cycle, which I think is okay here. So I'm not entirely sure why that's not working as I expect. So here's another downside about having a language like this. I don't have trace support. So I can't really see what count is unless I just export it now, which I could do. In fact, let's just do that. Just hack that, and then in here we can do like that. And I think that works if we run the test. Do we not get the... I thought we would get the output from the test like that. Remember how to do this. How to print during debug tests. Oh yeah, no capture, that's the one. Thank you. Yeah, and here it was 0, which is actually what we wanted. So then why did it think that it was empty? Assertion failed again, 155, which is this one. Empty should be true when count is 0. So that should... Oh, it was running with one capture. That's what you're saying, yeah. It did actually print that. That's great. Yeah, totally didn't see it. Oops. But I wonder why that's the case. Why it's not empty on the following one. Oh, I think I know why. I think I know exactly why. Because I think it's the test that's wrong. The test issues this write and a read. And then on the next cycle, it doesn't deassert the write. So I think if I do this, then it should be empty again. Because it didn't think it was empty because we were still asserting a write. So now the test actually passed. So I feel okay about that. I don't trust this fully, which is why I wrote this other test that pumps a lot of data through it. And so I want to run that too. And I think I do that by do cargo run. We want to do this in release because this is stupid slow. For the seed, we can do anything. And then we can just do 100 elements to start because if there's an error, it'll print out everything. So that should make it relatively easy to spot, or at least possible to spot. So this is kind of one of the issues, is that it can just hang. And that usually means that the writer was able to write all of the data. And then the reader didn't read all of it. So this thing just hangs, which is a good enough test case. I'm happy with it hanging rather than like as a failure mode than anything else. So, but I actually need to BRB for a second, so I'll come back shortly. And I'm back. So yeah, the question is, how the hell do we debug this, right? And so I have a couple ideas. One of them is actually just hack trace output. First thing I'm going to do, though, is just drop the number of elements and see if we ever get everything through. And it doesn't seem like we do. Which is a bit surprising with just one element. Especially because this should only affect whether or not it's able to do reads, right? So it might be... Let's see. It might actually be the test. Because if it doesn't... If it's going to propagate a write, I think we actually need to do m.prop here. And that might explain it. Because now, whether or not we're propagating a read actually affects whether or not it's going to be empty, which affects whether or not we think our read was successful. So it might be this. And if this is the change we have to make, that's actually great, because then we don't change any of the logic. We only change when we propagate signals. So I'm quite pleased if that fixes the issue. And it does for that case. So we might have lucked out here and not even needed to do traces. So I'm just going to crank this up, and we should eventually see it not break. Just until it takes a while, and then I can kind of trust it. Right, so now we have a nice high number. 10 million elements. And we can do this. For seed in 1 to 100, do this, done. And hopefully this doesn't use a lot of CPU and wreck my stream. I don't think it should, because it's only single threaded. And you can see the cycle counts are slightly different each time, and that's a good indicator that this is actually somewhat randomized. But this is great. I think this is a great way to fix this test, because now, again, yeah, you guys get it. I think this makes sense. So I'm pretty happy with that fix. I don't think it's very visible in this test that this should actually be like faster, but it should allow us in the case where the Fifo is like initially empty, it should allow us to get data out of it a cycle sooner than otherwise would be possible. So this is purely a latency improvement in the cases where we're going to use the Fifo, not a bandwidth improvement, because if the Fifo were actually saturated, or if we had a constant stream of things going into the Fifo and a constant stream going out, then it would only subtract a single cycle of latency, which I think is also why we don't see that the cycle counts have changed, which I don't think I ran this before I made this change, but the cycle counts roughly looked the same. So I'm going to also run this for several hours later, but I feel pretty good about it already. This is pretty good testing, and this is not a very complicated module. So this is great. Looks like it works. I think I'm going to commit this. Shouldn't be that much difference here now. Oh yeah, and there's this debug count thing that I don't want to print. Again, just be sure I'll do a cargo test. Of course, this should work. Yeah, we're fine. Great. Yeah. Cool. I'm already happy with that. If that's all I do today, I'm pleased. But let's see. So I haven't had time to make proper diagrams for describing the memory topology that I actually want, or I guess the bus topology that I'm after here, because it has somewhat changed since the last iteration of the xenowing. And the main thing is that I think it was in November I decided that I wanted to have DMA support, and in order to do that, I need to have a somewhat more complicated hierarchy for the buses. So I have just a drawing in one of my notebooks here. And I'm just going to attempt to kind of redraw some of it in a really ugly way, but it's going to be fine. So the idea is that I have this display DMA, which we'll call DD. And this needs to read. I use arrows to say that this is a read port. That doesn't necessarily mean that all the data flows this way, because there's some signals for like handshaking. So there's like, this needs to send the address, for example. So the arrow only means that this is the direction that actual data is traveling, even though there's signals as part of this arrow that are going to be both ways. This is connected to, I think, what I call the memory bus, or maybe the RAM bus. And this will actually connect to the RAM itself. This is just an interface over the RAM. And this is DDR3. Looks so ugly. But it'll get the point across, right? So also connected to this is going to be the DMA. And this is going to have to be able to read and write to the RAM bus. And also, there's the system bus. And so the DMA also needs to be able to read and write here. And then we have the CPU interface, which is up here. And the CPU also needs to be able to read and write from the RAM bus, and also from the system bus. And then down here is where stuff starts to fan out. So if we have like the LEDs, we have the GPU, all this other stuff. And all of this is going to be connected through the system bus. And the main thing that this kind of design encapsulates is the fact that each of these buses down here needs to be able to support reads and writes from different bus masters. I think I also need to draw these arrows this way. Actually, yeah, that's correct to do it like that. And then the DMA in particular needs to be able to simultaneously access both of these buses. It needs to be the master for both of these in order for it to move data to and from RAM to these other peripherals here. So the way you're going to move data into the GPU's local memory, it's a tiled renderer, so there's going to be a small amount of memory here. Essentially what you do is for every tile, the CPU is going to tell the DMA, which I think that also means, no, there's not a connection from the CPU to the DMA that actually works like this. There's a DMA control here. Which is actually, will do register writes to the DMA as kind of another bus that's not shown here. So these, you can kind of imagine this like this, and then there's additional connections here that you don't see. So that's how the DMA is driven, and that's also how the display DMA is going to be driven. So it all kind of works out. This does technically mean that the DMA can end up writing over its own control registers, which would be really bad. But I'm going to allow it because disabling that means I have to support even more buses, which is going to get really complicated. So I think this is kind of the most minimal design that captures what I want to do, and that's what I'm getting at. I feel like I got a bit lost on what I was talking about. But yeah, the DMA needs to be able to access both these buses simultaneously. And there's also some priority here. So for example, the display DMA is going to be really timing critical. That's basically every scan line that we're going to output pixel data that needs to go and read the RAM and get that pixel data as soon as possible. So it's going to load that into some buffer that's also being read from for the actual display hardware. But this needs to be like the highest priority are these reads for this RAM bus, and then the DMA, and then the CPU. But at any given time, like the CPU could be reading and writing, and then it might trigger the DMA through some of those reads and writes. So it might kick off the DMA, and then it might even get a cycle or two where it can write something to memory. And on the following cycle, maybe the DMA kicks in, and then this is moving data between these two. In the middle of that, this display DMA might start reading, and then that needs to take priority, and then that needs to read a bunch of stuff from RAM. And then when that's finished, then the DMA can finish doing its job, and then the CPU can kind of resume. So I need something that can handle multi-master like this really effectively. Now I've started here. And the reason I've started with this part is because it only has one slave. And that simplifies a lot of things. This one's going to be, the system bus over here is going to be a slightly more complicated version of the same thing. Where I basically take whatever I implemented here, and then I remove this extra read port, and then I add a bunch more slaves. So I think I've more or less come up with a design that will work that I basically explained earlier in the stream. But yeah, we're doing sort of the simplified version for just this RAM bus part. So if I make a new drawing here, and by the way, I will make proper diagrams for all this at some point. I just haven't yet. So we're getting paint today. You guys are used to it anyway. So if we kind of draw this a bit differently, so let's say this is that RAM bus, and I'm gonna draw on its side, and we're gonna have a couple input ports and a couple output ports on one side. So these are gonna be the masters. And then over here, we're going to have the slaves. And I'm also only focusing on reads for now. Because I'll do reads first, and then I'll implement writes on top of that. So for reads, there's only one return. This is the slave. And there's actually two arrows here, because here we are actually drawing like the issue signals and the stuff that comes back. But there will still be some signal grouping here. So the idea here is that I have two masters. So I have master 0 issue. We're going to call this issue and return. And then the master 1 issue. Master 0 return. Master 1 return. So the idea is that these are the two masters that are issuing reads, and then eventually the data will come back through one of these buses, depending on who issued the read. That's the idea there. And the reason why I draw it like this is because we're basically gonna draw a dotted line through all of this. And I should have drawn this arrow a little lower. That's fine. So on the top here this is the issue up here. And then down here we have the returns. And so what I've come up with here is there's the issue arbiter, which we're going to call IA. And that's going to sit here and do the priority stuff. So it has these two things that might be trying to issue reads for a given cycle, and it's going to have priority there. And what that's going to do is once one of those has decided it needs to issue a read, then we have the issue buffer. And that's where the data for that read is going to be buffered here. Now, if this read is actually able to be issued because the slave might actually be busy, for example, doing RAM refresh, and then we can't send it any more commands, so that needs to come back. That's why we buffer this, is because it might need to be stalled. But if this issue is successful, it's going to go out here. And this I call, I think, slave issue and then slave return. So once that's issued, this is going to do this. And then also we're going to have, it's going to issue the actual data to issue the read. And that's also going to do some internal bookkeeping in this Fifo here. So we're going to call this Mem Fifo. And the idea here is that it's going to issue the read. And in addition to that, it's going to dump whichever master issued that read into this Fifo. And eventually what's going to happen is the data will actually come back. So we're going to bring that back in here. And I think we'll get to what that does in a second. But eventually there's also going to be another buffer here. Just going to call the master buffer. So again, the master here is in this case, since there's only two masters, this is a one bit signal that determines for a given read, right? Because there's a Fifo here. So we issue a read, and then we also issue which master issued that read, right? So in the case that 0 got a read through, then this is going to be 0. In the case that 1 got a read issue, then this is going to be 1. So this fills up, and then this pulls whatever the head of that buffer is into a buffer. And the idea is that eventually when data comes back through this SR thing, we can then take the data and match it with whatever master this is and then send it back out here. So I think I have this return arbiter. Return arbiter that then will decide where the data goes back to which one of these masters. And the last thing we need, which is why I wanted to fix this Fifo thing, I'll explain why, is, so let's just imagine this. Let's imagine that on a given cycle, the read was able to be issued. So we dump, we issue the read, and then we dump the master thing in the Fifo. Now let's say in that same cycle, because now we've enabled write through on the Fifo, on that same cycle, the read is issued into this buffer. And we're going to assume also the lowest latency possible for the slave. So if it were 1 cycle. So on the following cycle, the data will be read out into this buffer. And the data will come back in this SR thing. So if that's the case, instead of matching the data here, we need, because the data is going to be written into here, we need to actually buffer this. Which I think I called slave return buffer. And so again, the idea is that on a cycle, data goes out here and into this Fifo. On the following cycle, data comes back and comes into this buffer. And then the cycle following that, the arbiter can pull data out of both of these buffers and ship it on its way. So this should work fine and dandy. And this was kind of the original picture that I drew. And I feel okay about this. I think this is going to be a good enough design. Again, it serializes all the reads coming back, but that's only to, well, in this case, it's a single slave. So the reads are actually naturally serialized by the fact that the slave will only ever issue or return data for reads in the same order that the reads were issued. But we still need to know which master sent the data. So that's why we have this Fifo. So this should achieve some kind of peak throughput. And then I think I figured out when I started implementing it that like this buffer actually doesn't need to be registered. So data just comes in here pretty quick. But if we didn't have write through on this Fifo, this is kind of the issue and why I needed to fix this. If we didn't have read through on this, then what would happen is let's simulate a read happening here. So read comes in, let's say it's this one, and the arbiter says, yeah, that's the one we want to issue. So it goes into this buffer, and then this says, yep, I'm ready for read. So we issue that, and then we put this in our buffer. Right? Now the following cycle, which I'll use a different color for, just to try and make this a little clearer. On the following cycle, let's say this came back. The data came back into this buffer. And then let's say on the following cycle, we were also able to issue another read, right? Which can happen. Then we have more data going into here. Now on the cycle following, if we didn't have read through on this FIFO, that's actually when this data would get, when this data actually gets loaded into this buffer. And actually I need to draw this slightly differently. Right, so we got to go back in time here. So we issued the read, right, and it went into this buffer. And because we don't have write through on the following cycle, this won't get loaded into this buffer. But if the slave were really responsive, then this data would come back on the following cycle and fill in this buffer. Now, if on that same cycle that read came back, we were able to issue another read. No problem. This is valid. Now on the following cycle, this would get the data ready for this read. But then what would happen is the slave would come back and say, hey, I got more data. And then if we only had this one stage here for this buffer, then this data would get overwritten. So instead of containing this blue data, it now contains this green data. So then what would happen is on the following cycle, this would say, okay, great. Let's send this green data to the blue master, right? Because that's the data that it has. And then this is really bad, right? Because then we get the wrong data going back here. And then on the following cycle, the green master comes into this buffer. And then this actually never gets filled with correct data. So now not only have we sent the wrong data to this first master, but then this whole thing will actually deadlock. So this is really bad. I think it actually won't deadlock because I think the next read issued would actually get returned with this data. So as long as we can still issue reads, but if we never issue another read, then this will never return, and then this is really bad. Does that make sense? I know I'm not explaining this the best, but I know it's a real problem. And so one of the reasons why I wanted to tackle that at the FIFO level is because, first of all, then I don't have to add additional buffer stages, because what I could do is I could make this a FIFO. With this return buffer could also be a FIFO. And then I could have another buffer there. So if I had a parallel FIFO here, then it would make sense. But I thought if I solve the write through problem on the FIFO, then not only do I get lower latency every time I use the FIFO, but then I also don't need this secondary FIFO, because then let's go back in time. Because now let's go back to this blue one when this initial read was issued and we stuffed the master into this FIFO. Now on the following cycle, the data is going to come back and this data gets loaded into this buffer. So this and this happens on the same cycle. Again, best case, or I guess worst case for this implementation. Now during that same cycle, we could, for example, issue another read. So let's say that's happening the same cycle. And again, this goes in here. Then on the following cycle, we have something in this buffer. We have something in this buffer. Great. We're going to merge that here and send this on its way. We're looking good. In that same cycle, the green data comes here and this green data can come back. And then on the following cycle, the green data gets merged in this arbiter and goes on its merry way. Great. That's what we want. And as long as we have write through on this FIFO, it should be possible to implement this. However, if we didn't, or not if we didn't, let's consider like one more case here. And that's the case where, again, we go back to when we were able to issue this read. And then let's say on the following cycle, the slave took more time to come back with data. Now let's say, for the sake of argument, that it took, 2 cycles. Then on the following cycle, this gets loaded into this buffer. And let's say we also had the case where we issued another right here. And let's say the slave could handle that we could still issue another read. That goes into that FIFO. Now let's say let's say n number of cycles later, it really doesn't matter as long as it's more than 0. So 1 cycle later, let's say, the data comes back. Now that's actually fine because this has just been waiting in this since the FIFO stores the data for this other green write too. And also there's some blocking here. So if this FIFO gets full, we won't actually issue writes, so that won't be an issue either. But now in this case, that's fine. So on the following cycle, again, this will all get merged, and then it goes out the proper one. And additionally, in the following cycle, the green one goes back into here. Now let's say during that same cycle, the green data came back, which I think it would actually come back on the cycle following this, which again, it wouldn't matter, because then as soon as this has both some data in this buffer and then a master in this buffer, then those will be matched again and go out here. So I think this design holds up. That's kind of what I'm getting at by walking through a lot of these use cases. I think this design holds up. But again, a critical point of that is that we need this Fifo to support write through, which now it does. So it's glowing. Again, we could have worked around this also by adding another Fifo for the return data, but why do that if we don't have to? Now the other thing I noticed is that even though I kind of drew this out, I really had to think through all these cases. Like it's something as simple as this one bus, which is, I mean, it is pretty critical to the operation of the console, but this was not a problem that I expected to spend so much thought on. But I think it's actually justified to engineer this much, because we need this to be rock solid and we need this to be testable. And again, I don't think this design conceptually is that complicated. It's a bit annoying trying to like track the data through and the different cycle counts, but again, we can write very specific tests for all those. And I can also set up like big random tests for this relatively easily. So I think this is going to be good. And I think it's going to work. Now, this does get a bit more complicated once we have multiple slaves, which is what the next part of the bus is going to have to deal with. And in that case, we are actually, instead of just having buffers here, we are going to have a buffer, one of these buffers per slave and a Fifo per slave, because then we need to, if some slaves are faster than others at returning data, we essentially need to throttle that input until we can get the earlier reads out to the correct masters in order to match them. So that's going to get a bit more complicated, but should be a relatively natural extension of this. And then the other thing that I didn't talk about here is, what if these are issuing writes in the meantime? And that, I think, is just a non-issue, because if it can issue writes, all this buffering and everything is still going to block the write, except I think we can issue writes without caring if this Fifo is full, which is nice. So writes can kind of just slide in here unnoticed. And then the rest of the system doesn't have to care, because the slave's not going to return any data for writes. So writes should be a trivial extension is kind of what I'm getting at. I want to test the reads and make those rock solid, make sure that this kind of strategy works. And then once I know that that's the case, then I can add writes and test those. That's what I'm thinking. And then eventually too, it might actually make sense to implement both of these buses the same way, where I actually do have a Fifo for this slave. And then maybe I implement it in a really generic way that you can add n slaves and n masters, and it will kind of figure out a lot of this work for you. I'm not sure how feasible that is yet. Need to think more about that. But I thought what I would do is I would write what I need first in kind of a lower level way. And then if that ends up being all I need, then I'm basically done. And then if I want to look at abstracting that more, I can do that, backed by all the tests that I'm going to write for these. So again, I think that's the right strategy here. But yeah, even when writing this, I found it was difficult to write, because, like, again, it's not terribly complicated, but it's the interaction of all these different pieces can actually be a lot to keep in my head, at least. So I started. One of the reasons I broke it down into all these little functional units and made this kind of pipeline diagram, which again, I'll get rid of all these little reads so you can see that a little more clearly, is precisely for that reason. I just had a really hard time imagining all the different signals, because even though there's just a few arrows between a bunch of these arrows are not just arrows. It's this Fifo, for example, needs to send if it's full or not here. And then this needs to send if it's ready or not here. So this has to deal with all of that and all the different interactions there. And I found it a lot more natural to think of these as individual pieces. So this just handles arbitration, and then that's really easy to deal with. this just handles this buffering. So it'll react if the FIFO is full, it'll react if incoming data is trying to come in here, and it'll react if with the data here and then issue. So it just handles that. The FIFO is just a FIFO. The buffer, its only job is to get stuff out of the FIFO, basically. And then if this arbiter tries to go and clear it, then it needs to, again, try and get more stuff from the FIFO or just be empty. And same with this return buffer. And then this arbiter is pulling data out of these two and then passing it on. So yeah, it really is Artemis. And it's one of those things that I'm finding is continuously hard. Like or consistently hard for me is to imagine the interactions of these things over time when you're looking at these on a signal level. And I think also that's just one of the reasons why people do hierarchical design like this in the first place. But I guess what I'm finding is that I have to do that too, which not really a bad thing, but takes a bit more upfront design work than I would have imagined. But again, that's fine. Kaze is a good enough language to implement this stuff in. Like I don't know that all this is correct because I haven't tested any of it, but I was able to write this issue arbiter. So again, this has these bus enable and address signals. And then it also says if this issue buffer is ready to accept input. And then if it is, it's going to try and actually pass on these signals. In fact, I think the arbiter, does it even use this? Yeah, it needs to use, it needs to return if, because these also need to have some like throttling logic. There's some additional logic that you pass back here, which basically says if this whole RAM bus is ready to accept data, and you need to generate one of the signals for both of the masters. And the conditions for which master you do that for actually change because that's how we implement priority. So if M0 and M1 are both trying to issue a write, I'm going to use a fixed priority scheme where, like, for example, M0 always takes priority. So if both are trying to issue a write, then you actually need to accept the write from M0. So you need to tell M0 that I'm ready to accept data, and then you need to tell M1 that you're not ready to accept data. So that's why I have this master 1 bus ready thing that's dependent on whether or not master 0's bus enables is high. So again, it's those subtle interactions that I don't think are that complicated to describe in isolation, but when you're looking at all of this, it very quickly you get lost in it, or at least I do. So I think it was a good idea to break this down. So I've implemented this arbiter. I think I've implemented this issue thing here, and again, I think I figured out that it actually doesn't even need to be registered because I think I could just do all of this stuff with combinational logic, which is nice. And then all the buffering happens in these other components. The FIFO again is just a FIFO, so that will basically work. What else did I implement? Yeah, I started with this master return buff, which is this one. It didn't get very far, as you can see. And then I also tried doing the slave return buffer, which is this one. And I could also do individual tests for these smaller modules. It might end up that I actually do that. I was hoping to get away with not doing it, but it might make sense to do it at that level, actually. And then I don't think I've done this return arbitration. No, I have not. But I did make the FIFO and issue that and hook up a bunch of stuff. So I think if I run this, because this was just in a separate project, in a project called Buster, I think. And right now it doesn't actually simulate anything, but if I do cargo run, I think it will generate the code for all this. So I don't know that this code is correct, but it does get generated. It's correct enough for that at least, which is the first step. Oh, I had to sneeze for a second. Maybe it's gone. I've been sick earlier in this week too, by the way, which I hate because especially when like I'm making a lot of really good progress on this project, and a lot of stuff's going on at work, and so it's like it's so frustrating to just be able to sit there and not be able to think of stuff because I just don't have the mental bandwidth when I'm sick. I hate that feeling so much. And so it was last night when I finally started feeling better that I just went nuts on this because I finally could, and it felt really good. And it's nice to see that this looks as straightforward as it does because I felt a little loopy when I was writing it. But again, that's just a testament to being able to break it down and work on it hierarchically like this. So I might as well just sit down and kind of continue on this. Again, I think this design is more or less correct. So let's see. I do want to check over some of this code though, so I think I'll do that. And maybe that's a good thing to stream anyway, so you guys can kind of see all the different signals that goes into this, at least what I have imagined so far. So this issue arbiter, again, takes all of the input signals from the masters, and that's mostly this enable. So there's some like bus protocols where you have like a write request and a read request line. And that's actually something kind of subtle that I wanted to talk about too. I'll draw some pictures over here. Do I have room enough for that? Or is that below my... Good, that's good. So if you look for... We'll take the write request and then the read request. Make a little truth table here. No. Write request. Because you have 0, 1, 0, 1, 0, 0, 1, 1. And I guess the main thing that I want to point here, I actually did want to draw it the other way. Like this. So you have 0, 1, 1. So yeah, so this is 0, 0, this is 0, 1, 1, 0, 1, 1. So the interesting thing is, if you look at this, if neither one is asserting, if we're not asserting a write and we're not asserting a read, that's a valid state, right? If we're not asserting a write and we are asserting a read, that's a valid state. If we are asserting a write and we're not asserting a read, that's a valid state. But then here, this state's actually invalid. This means we're asserting a read and a write, which the way I've designed these buses and the way that like Wishbone and Avalon and stuff do it, you can only ever do one at the same time. So it seems kind of dumb to me to have these two be the signals that you would assert, because it's possible to make this invalid state. So what I decided to do is take the same two signals and replace them. So instead we have enable and then write or read, I should say. And then what this means is not enabled. Let's say we'll put enabled first here. So not enabled and not a read or write, doesn't matter as long as it's not enabled. That's a valid state. Not enabled, and let's say 0 means read, or 0 means write, and then 1 means read, which I think is how I have it in my head. So in this case, not enabled and a write is fine. We're just not going to do anything. Not enabled and a read is fine. We're not going to do anything. But those are still valid states. And then here we have enabled and a write, which is a valid state. And here we have enabled and a read, which is a valid state. So here it's actually impossible to describe, to assert these signals in an invalid way. So I changed it up to do that. And the other reason I did that is because I ended up, when I had write enable and read or write request and read request signals as separate signals, I found that I was writing a lot of logic where I would just OR those together to determine if the bus was, if the master was trying to interact with the bus in the first place. So this kind of solves both problems where, one, we've masked out invalid states, but also all that logic that I kept making to check if the bus was being interacted with now is natural, like that's part of the bus signals already. So so I'm pretty happy with that small kind of aside there. And all that's a really long form way of saying that's why we have enable signals for both of these. And again, I'm only focusing on reading for this initial implementation, and I'll add writes later. So, because again, reading is the complicated part. So yeah, so we have these enables and then the addresses. And we also have if, again, this is just for the arbiter here, if the issue bus ready. So it's basically, this sends a signal back to say if this bus is actually ready. And so if master 0 is enable, then we want bus enable and the bus adder to reflect master 0's enable and adder. So if master 0 bus enable, then we know its bus enable is going to be true. And also these true 1, okay, I was a little loopy, wasn't I? These should be m.high, first of all. And I think I have a bunch of these false ones too, which should just be low. That's kind of funny. But yeah, and then in the case that master 0, its bus is not enabled, then that means master 1 has an opportunity to interact with the bus. So then we say the bus enable is going to be master 1 bus enabled, and the address goes with that as well. In addition, we have this bus master, which identifies which of the two masters, if like a read or write got through, which master was it. And in this case, we say master 0 is going to be 0, master 1 is going to be 1. And then finally, there's this bus ready. And this is what we're going to send back to the masters. So the idea is, this might be wrong actually already. That's great. It's a good thing we're looking through this. So in this case, if master 0 is bus is enabled, then we want to do... Oh no, this is the master 1 bus ready. Okay, this is actually correct. Yeah, so if master 0 bus enabled, then we know that master 1's bus ready is going to be low. So we're disabling that. We're telling that other master that the bus is not available whenever master 0 is trying to interact with the bus, which is what we want. And then in the case where master 0's bus enable is low, then we want master 1's bus ready to reflect the bus ready. And then I think for master 0, we always just pass this bus ready signal through, because if it's not trying to interact with it, it doesn't matter that it's getting this ready signal, even if it's not using it. It only matters if it's trying to interact, whether or not it will do any logic based on the signal. So we always pass that through to master 0, and then master 1 again. We might cut it off if master 0 is trying to use the bus. So I think, again, that this makes a lot of sense. This looks good to me. And then again, this just outputs those signals for the next stage. So if we're actually trying to interact with the bus, which master is actually doing it, and then the address that it's trying to read from. And then again, we send back to the masters if the bus is ready. So that looks good to me. And now we'll look at this buster issue. So its main thing is to say, okay, if one of the masters is trying to interact with us and the Fifo is not full and the slave is ready to accept data, then we will actually issue the read and pass the necessary information for the read, which I think is just the address, to the slave, and then also pass the master information into this Fifo. So here, you can see I take some of these signals, which is this signals that are going to be output from this arbiter. So there's this bus enable, and then which master it's going to be, and then the address. In addition, I take in a signal to see if the slave is ready. And then also I take in this master Fifo write ready, which I called write ready, but really it's full here. And in fact, what I think I actually want to do is do this. Cool. So we're going to do something here. Master Fifo full. I think I want to formulate it like this. So you can see basically here I do the same thing. But I think on outside of these modules, I just want to do just dumb signal connections, and then inside I can actually interpret that signal, right? So the idea here is that I take in whether or not it's full, and then I determine whether or not it's ready for writes based on that full value. So I think this actually makes more sense to formulate it that way. Anyway, the point is, if the slave is ready to accept data, and the Fifo is, and we're ready to do writes, and bus enable is here, then we actually want to do the write. So here, first of all, we want to return this ready signal, and that comes from if the slave is ready to accept data and the Fifo is ready to accept data, then the bus is ready. If either one of these conditions is not true, then we don't want to tell the master that this bus is ready. Eventually, this signal is actually also going to be dependent on whether or not the master is trying to assert a read or write, because again, on writes, we don't care about this Fifo being full. We only do on reads. So there's some potential performance improvements here that we can take advantage of. Because as the code is now, if we added writes to this directly, then all writes would also be blocked on this Fifo being full, which again, wouldn't matter. So we'll want to fix that. But again, doing reads first and then writes. Just sharing out loud because a lot of stuff is going on in my head when I'm thinking about this. Anyway, so I think this is correct, because I think those are the only two conditions where this matters. And then for whether or not we issue a read to the slave, that depends on if the master is, or if the issue arbiter is telling us that the bus is ready and the Fifo is ready. And if those two are the case, then we want to tell the slave, we want to issue a read to the slave. Now, an important thing here is that we still want to tell the slave that we're issuing a read, even if the slave is not ready. which I think I showed in one of these diagrams before, where it looks like I got rid of it. Maybe my other diagram had that. Yeah, this will work. Basically a case like this where here the bus is trying to assert a write, or actually read in this case, but the bus was not ready. And we still want to assert that read. It's just that we won't finish asserting it until we get a cycle where the bus was ready. So that's what I'm trying to capture here. That we still want to pass through enable whenever we know the master wants to and the Fifo is ready to accept data. So I think this makes sense. And then we're always going to pass this address just through to the slave. Because again, if it's not issuing a write or whatever, it doesn't actually matter what this value is. So if we always pass the value, then that simplifies our logic. And then whether or not we actually write to this Fifo, that's going to be if the bus was actually trying to write to it and the Fifo could accept data and the slave bus was ready, right? So it's the same condition for whether or not we're telling the slave that the bus is enabled. But then again, we only write to the Fifo if the slave told us that it was actually ready to accept data. And then the write data is always going to be this master thing from this. Because again, if it's not trying to assert a read, we're still just going to put this data on this write data bus, because if this enable signal is not going to be high, it doesn't matter what this data is. So again, do the simplest thing. So this looks good to me. And again, I think this is a good granularity for actually breaking this problem down, because these are, so far as we've seen, these are not complicated units. But already you can see, as I'm trying to explain it, like I do have to think about it. So I think we reached a good granularity there. Now I'll get back to this master return buffer, which is this one, because I haven't written the code yet. So we'll just describe what I have done. And then there's this one, which is the slave return buffer. And this, I think, this has relatively simple behavior. So again, going back to this diagram, essentially all we want to do is, this has sort of two states. One of them is the value or the data that's in it. And the other one is this ready signal. I don't know if ready is actually the right signal for this. In fact, let's call this full. So essentially whether or not this data is valid. In fact, we could actually also call this data valid. Dave valid. Yeah, I kind of like data valid because you have data, and then if this data is valid. Yeah, I like that naming. So the idea is initially, it doesn't matter what this data is, the data is invalid. And then as soon as the slave comes back and pushes data into this, then the data is going to be valid. And we want the data to stay valid until we have a case where this arbiter here is going to issue a read. So it's going to pull out that data. And there's also another case where if it pulls out that data and the slave comes back with more data, then we want the data to be valid again on the next cycle. So it's essentially, it's going to be initially empty. If the data is valid and the arbiter tries to read, then we're going to make it empty again, or non-valid. But no matter what the state of this is, if the slave comes back, and this always takes priority, if the slave gives it data, then it will latch that data. So a bit more complicated here with the conditionals, but I think it's okay. So here we have, again, the read enable signal. That's if this arbiter is trying to pull data out of this buffer. And in addition, we have the data coming from the slave. So we have the data, and then again, if that data is actually valid for this cycle. And then we have the data and the data valid registers here. So the next data and the next data valid are going to depend on, because it's priority, then the top level conditional here is based on if the slave has new data. If the slave has new data, then regardless of any of the other signals, our next data is going to be whatever data the slave is returning, and our next valid signal is going to be 1. So if the slave's got new data, then we're definitely going to be reflecting that. If the slave doesn't have new data, then we have to look at what our what our read enable signal is going to be, is what the logic I have here, which makes sense, I think. So again, in this case, we know that the slave does not have new data. So if this arbiter is reading data from us, then we know we're going to be empty. And also we latch the current value. We just keep that in here. And then if the arbiter is not trying to read data, then we're going to keep whatever our previous state was. So if we're empty and it's not trying to read data, we're still empty. If we're full and then it tries to read data, we go to empty. But in either of those cases, if the slave has new data, then we take that new data. So I think that's it. So if the slave has new data, we also take its value. Otherwise, we keep the previous value, and then whether or not that's valid is determined by whether or not that data has been read by the arbiter or not. So I think that's okay. Hey, Dark Second. So we determine these data valid or data and data valid signals, what the next ones are going to be, and then we drive these registers with those signals. And then we output them too. We output the data and the data valid, which is the current value. So in this case, this buffer is registered. The data in there is registered. But I think, again, that behavior is not terribly complicated. So I think that makes sense. Now, coming back to this master return buffer here, I think that was the next one I started on. I think this one does get a little more complicated, but again, let's just start by kind of what we did here, where we're going to take these just look at the signals that go into this. So, by the way, is this the right thing we want to do here? Ret arb buff read enable. I'm giving this a long name, but it's because it's descriptive. Because this one's going to have something else, which is ret arb. This is going to be the master buff read enable. Master ret buff even. Yeah, so that's if this arbiter is trying to read from it. And I think this is the right thing to do, is to have this arbiter tell both of these when it's trying to read. It's going to do it based on whether or not this one has data, really. Because the way we've designed this, we're going to assume that if this has data... Well, I guess it needs to know if both of these, because it is possible that this has loaded a return master and then the data hasn't arrived yet. So that's actually true. So the arbiter is basically going to say if both of these have data, then we're going to output that data. Otherwise, it's going to output nothing. So again, I think this too is also going to be purely combinational, this arbiter here. Maybe it actually makes sense to tackle that part next, because I feel like that's actually a bit simpler. No, actually, let's just continue with what we're working on, one thing at a time. So yes, this master return buffer. If the arbiter is going to read from that, we need that signal. We also need, if the Fifo is ready, and in fact this, again, we're going to do master Fifo full. I also think master ret buffer, I call it master Fifo, so why don't I just call this master buff? Why not? And then yeah, if this is full. And so then we can also do this whole thing here. And actually it's not full that we want here, so we want master Fifo empty. Then we want to say let's master Fifo read ready is not master Fifo empty. What other signals do we need? Is that it? No, because we need the... couple things here too, like the let master Fifo, actually do it below here. Master Fifo read data. M.input. And the one thing that's going to be kind of complicated here is that if we know we're going to be empty, and we know that there's data coming in from the Fifo, we actually have to issue the write and then issue ourselves a signal to latch the data on the next cycle. That's kind of the thing here. So again, when this issues, this goes in the Fifo, and then that's the one where we issue the read. And on the following cycle, the data comes back into this buffer, and then this buffer will have like some read enable signal where we'll actually latch that data. That will happen on the following cycle, and then the following cycle, this has data, and then the arbiter can take data out. So again, I think the behavior makes sense. I feel like I'm talking more than usual in this stream, but it really helps me actually to talk through this. So appreciate it. Let's see. Yeah, so here we also need this data and data valid registers. And the data here actually just needs to be 1. I'm also going to output these outputs here. Let's see. Yeah, and then we need another register, which is let data latch is m.reg. And we're going to do data latch dot default value is also false or low. And then we're going to do this sort of same thing like this, where we say let next data valid is this if thing. And here it's actually if data latch, right? So if the data is going to be latched, then the next data is definitely going to be master Fifo read data. And then valid is going to be m.high. We're going to have this again. And then, yeah, and the same thing, we can keep the data, and then we just need to determine what the next valid signal is going to be. That's going to be this: if the return arb master buff read enable is high, then it's going to be low. Otherwise, yeah, the previous value. Data latch dot value is also what we want. Now let's see. As you can see, we're not using the signal. It's really nice that Rust tells us that. Let's see. I'm actually a little concerned about this. So the idea here, it's going to undo as much as I can here. if this issues a read, we want to get rid of this data. And on that same cycle, we want to issue write. Or issue read from here if we can. Man, you guys, we might actually need a Fifo here. Because then this won't latch the data until the next cycle. So let's say again. Let's say this had some data and this had some data. And so then this got read here and this got read here. And let's say on the previous cycle, we issued some more data. So this has a thing in it, and then this does this. So on that same cycle, this can issue a read to this Fifo. Then on the following cycle, data comes into here, and data comes into here. And it's not until the following cycle that data's latched here and data's latched here, which seems fine, actually. What's the problematic case? I feel like there's a problematic case here. What is it? Okay, let's say these both have data in them. Right, so how did they get that data? Let's walk through that. So again, we'll use this blue color. So first we issue this, and then we issue this. On the following cycle, because this was able to read and it was empty, this then reads. So following cycle, or during the same cycle actually, this issues that read because we have write through here. So on the following cycle, data comes in here and data comes in here. And therein, I think, lies the problem. Because once data comes in here and data comes in here, let's say on that same cycle, we issued another write. This is now no longer empty. So what's going to happen is it's not going to know to go read more data. So on the following cycle, because this and this have data, this is going to be returned. And at that point, this is going to go and reissue that read. And during that same cycle, the data is going to come back here. So it may not seem like a big deal, but this data coming back is actually going to be a cycle late. And that's going to be a problem if, in addition to that, we also issued a third read. It's maybe purple. Because then on the following cycle, this data comes in and this data comes in. And then we've lost data. Because on the following cycle after that, this is going to read green from here and purple from here. Okay, this design's not sufficient. There's a bottleneck in how this buffering works. That I need to think through. This would have come up in testing. I don't know if I'm lucky or unlucky that I thought of it now. And again, this has to do with this read latency coming out of this Fifo. Feels like we have like this one cycle latency that it's kind of like things bubble through this Fifo with a one cycle latency. And because this one doesn't have the same one cycle latency inducing Fifo. So even though we added write through for this, that only really works for that first cycle. And then after that, we get that other cycle bubble while we have to read from this Fifo while data is coming out of this buffer. And the thing is, we need this buffer because or do we? I was thinking we need this buffer because we need to determine the only thing. Yeah, wait, we don't need this buffer because all we need to know is, do we have another master coming, and then do we have incoming data? So actually, I think the issue is to just I think the solution is just to get rid of this buffer entirely. Because we already know if this FIFO is not empty, then we have a master. And if this buffer is not empty, we have data. And so what we can do is, if that's the case, if this buffer is empty and this is not empty, then I think this is still a cycle behind. It's confusing, you guys. Hey, Shodron, not sure how to say that, but how's it going? Yeah, I actually think we need another FIFO here, and then I think the timing just works out. Then data comes into this FIFO cycle early, but it's this issue here where when we read this, like we can't request more data out of this FIFO until we read from it. And if this arbiter tells the FIFO to get data, that data is not going to come back until the next cycle. So I think that behavior where we want to like output the data, that actually the arbiter needs to do that. And then I think if it would watch 2 FIFOs. And then I think we're okay. Because then data comes in here, and then like a cycle later data comes into this FIFO. And then as long as there's data in both FIFOs, then we can issue a read to both. The arbiter can issue a read to both, and then data will come out. So in theory, this one will always like lag behind. But I think it works out. I think it really just introduces a single cycle of latency up front, and then after that, this FIFO's like one cycle ahead, but it should still work itself out. Like we should still achieve good throughput. That's the point, even though we have an extra cycle latency, which we actually incur anyway by having this buffer. So I think that's what we need to do. Children, what I'm working on is a video game console that I've been designing for a while called the Xenowing, which is literally just my love letter to 90s video game consoles. So I'm designing this for FPGA, and we're not that far yet. I mean, I've got a working CPU, and now we're working on the system buses. So in particular, this is the bus that will sit between the CPU and also the DMA unit. And eventually there's actually going to be a third reader here too, which is the video DMA, but we'll get to that. And it turns out this is surprisingly complex because we have to interact with DDR memory, or essentially a bunch of different bus slaves. That's in this case only one, but a slave that can return data anytime. So as I'm walking through how this might work, I'm just discovering it's a lot more complicated than I thought, but I think I just solved it. So yeah, we're doing a system bus for a game console here. TLDR. It's really dumb that I draw all this stuff in Paint, but again, I'll have proper docs for this once it makes sense. The only thing I actually have that's better than this in actuality is notes in my notebook that I don't want to show in case I show something I'm not supposed to, because I also use the same notebook for work. So I just don't want to risk it. Anyway, I think then we have the master FIFO, and then we have the data FIFO. And then I think it's this. I think this is the design. Now, originally, I didn't want to do a FIFO here because I think just a buffer would have been enough, but I think doing 2 FIFOs just solves all these problems. Yeah, in fact, that allows us to basically get rid of this master return thing in total. So the issue arbiter, and then the issue buffer, those are the same. And then we have the 2 FIFOs. And I'm actually gonna like ignore a lot of the full or basically the full signal for the data FIFO, because if these FIFOs are the same size, then we can actually never issue more reads than would fill up this FIFO, which means no more data is going to return that's going to fill up this FIFO. So like we don't actually need to watch the full signal of this data FIFO, because this FIFO potentially becoming full will stop us from issuing, which will end up filling up this FIFO too. And then you can see the data flow here is really clear, because we're always going to be issuing across both these channels, and then this just gives us like a skid buffer while we wait for the data to come back. Yeah, I think this is really good, you guys. Yeah, so we have the master FIFO, and then we're also going to have this. So let data FIFO. This is the master FIFO depth bits, which is now just going to be FIFO depth bits. So the data FIFO, we're going to do this too. So we need to actually generate it. And this needs to be the data bit width, which I think is 128 for this bus. So this is also, I didn't want this to be a big FIFO because it's going to be big, but I don't think it's going to be that much actually. So this is going to be m.instance. This is going to be the data FIFO, and then this string here. Oh, sorry, Shodron. I totally misunderstood your question. I realize now that you said you have a question that's not on topic. Can you ask? And the answer to that question is yes. Feel free to ask. I thought I was spacing, and I totally thought you asked what is the topic of this video. I totally misread your question, so sorry about that. Yeah. So then we do. Let's see. We actually don't really have much inputs here. But we actually will do this. We'll do the data FIFO.drive input, and this is going to be write enable, which is going to be the m.input, and this will be the slave read data valid. And the data FIFO.drive input, which is going to be the write data, this is going to be m.input slave read data. And also these inputs need widths. So this is going to be the data bit width, and then this is going to be 1 for those widths. And that's it. We're going to also ignore the full signal for this FIFO, and then there's going to be the empty signals we need to fan out to this to the arbiter. Yeah, also this buffer slave, this slave return buffer also goes away. So we'll just read this code. Yeah, this gets a bit simpler. So now this is just going to be the buster return arbiter. Did I call this arb or arbiter? I think I called it arbiter. But I think I abbreviate some other stuff. Like here's the issue arbiter. There's issue. And I'll call this return arbiter, but then I'll do ret arb in a couple places. Okay. So yeah, I think this gets really easy because we have the let master FIFO empty is m.input master FIFO empty. We also have let data FIFO empty is m.input data FIFO empty. This gets so much simpler, you guys. A stupid buffer. I thought I was being clever. I'm glad I thought through this and was able to explain this to you guys, because that really helped me to realize that was a bad design. So yeah, master FIFO read ready is going to be not master FIFO empty. And we're going to do the same thing for the data FIFO. Yeah, these are going to be 1-bit signals. That was the error there. Okay. And then let's see. that's basically it, actually. Except we need to, when we issue the read, the data from these are both going to come back a cycle later. So we do want to handle that. So master FIFO data is m.input master FIFO data, which is going to be 1-bit signal, and then the data FIFO read data. I think I'm going to call those read data, not just data. Is m.input data FIFO read data, and that's going to be the data bit width for this whole bus. And then, yeah, we need a register here. Now we're basically just going to reroute the data signal straight through this. However, we are going to need to mux those with the master value, but that's going to come in like the next cycle. So we essentially need to do, I don't really know what to call this. We can call this read issued. Or let's call this FIFO read data valid is m.reg. Like that. Yeah, I think that makes sense. And so initially this is going to be false, right? So no reads valid initially. And then let's see, we're going to do drive next. So next value for this. Yeah, and I think this is just if the master FIFO read ready and the data FIFO read ready. So if both of those have data, then we're going to do this. So we'll also do this. We'll do let FIFO read enable is this. So if they both have data, if they're both ready, then we want to issue a read. I think that's good. And then we're also going to drive this register with that next one. So in fact, I'm even going to put this up here. Just organizationally, I think that's cleaner. And so then I can even do m.output master FIFO read enable. It's going to be FIFO read enable. In fact, let's just output this directly, and then we can fan out in the instantiation. So if both of them have data, then we want to read data from both. If either of them don't have data, we want to hold off. And then if we have issued a read, then on the next cycle, we want the data valid to be like this. And so then we want to do m.output yeah, we also need to do the arbiter stuff. That's true. So I don't think this gets very complicated because I think we say m.output master 0 read data, and that's going to be, let's say, the data FIFO read data, which is going to be valid on the cycles where that matters. And this, we can output this for both. Both masters can always get the same data. And then whether or not each one is enabled is actually really easy too. Because we can do m.output master 0 read data valid is going to be the master FIFO read data. First of all, if the data is valid and not the master FIFO read data. So the idea is that if the master FIFO gives us 0 and our data is valid, then we tell master 0 that the data is valid. Otherwise, this is the case for master 1. Oh yeah, I need to do dot value here because registers are not signals in Kaze, so that makes sense. Think that's it. So then let's actually instantiate this down here. I even called this issue arbiter. So let's call this return arbiter. Looking good. I'm thrilled if this ends up being more or less this easy. Because this is going to be a really easy design to add more slaves to. In fact, it's basically the same since we already have the FIFOs per slave. Then as we add additional slaves, we just add more of these ports. And so then this buffer here is going to need to know which slave a thing went to. And then this master FIFO is going to be extended to 2 bits. So it's going to actually be a master and slave ID FIFO. And then the idea is that we're gonna change which of these data FIFOs we actually read data from, depending on what the value of this master one was from. So that is actually going to be a little bit more complicated, because then I think we have to read out the master FIFO before to find out what the data was. Which I think that's where the idea for that buffer actually came from. But again, I'll deal with that later. And we also have writes to do for this, so we're not really in the clear yet. But yeah, there's a return arbiter. So for the return arbiter, we'll just go ahead and start going through some of these signals. So the return arbiter dot drive input. Here we do all the hooking up stuff. You need to come up with a less verbose way to do this, but for now it's fine. Master FIFO dot output, and this will be empty. And then what was this? Master FIFO read data. And this should work for the data ones too. Oh yeah, I don't need that went away. Yeah, because now we have the issue arbiter, issue, master data FIFO, and then return. So 1, 2, 3, 4, 5. Same out. Good. And then, yeah, I think here we have this read enable, which we're gonna drive from this now. Like this. This is gonna be return arbiter dot output. That's gonna be master FIFO read enable. And we're going to do the same thing for the data FIFO. Actually, yeah, it's the FIFO read enable. We called that here. So both of these, this is going to be FIFO read enable. Fine. So we have empty read data. And then enable. And then we need these outputs here. Now this becomes really nice because we're basically just going to do m.output for this module here, master read data with the return arbiter dot output of the same name. And we're going to have read data valid. And then we need to do this for master 1 as well. I think that, and then being able to adjust this depth might be it. So let's see if I made any mistakes. I still might have, but at least it generated code for all this. And you can see it even generated code for both Fifos, which is actually kind of cool. In fact, I think this is the first time that I've done this where I have Fifos as instances within a higher level module, which should work, but I don't think I ever tested it. So at least it generates code, and it didn't report any errors. So I would expect this to actually build, but I haven't actually tested it. So that's very cool. As far as actually testing this, I think I'm going to cut off the stream now. It's been a while. And work on testing this on my own. So I'll probably come back next week, and maybe this works. Maybe it didn't, and I had to come up with some stupid way to debug it. Maybe I'll share that. Maybe I'll have worked on the other buses. We'll see. I actually ended up having a few plans this weekend and got some stuff to take care of. So who knows how much progress I'll make, but at least I'm really happy with the progress today. So let me maybe push this really quick. Plus. That, and then I think we're good. All right, thanks guys for hanging out, and I'll see you next time.